y'all could put your cameras on so that I could take roll, and if possible, leave them on for class. And I understand some of you can't leave them on for class because of the connectivity issues. There you are. Oh my gosh, I'm so happy to see you. Several students asked about the instantaneous rate of change. We are starting, actually we're starting back a step today, but we're kind of covering that again today. Yeah, you're right on time, Christopher. Okay. Un momento while I pull up our attendance thingy. There it is. Okay, sorry, everything is being slow this morning. Again, if you're in any way able to put your camera on, at least for a few minutes, I sure would appreciate it for taking the roll. Luke, are you there? Ian, are you there? Alex? Ernesto? I see Alexis. I see Blossom. Joey, are you there? No. Brendan? Santiago, I see you. Christopher, there you are. And there's Victoria. I see Danny. I see Felix. Tiffany. Tiffany, am I seeing you, Tiffany? I do not see Tiffany yet. Okay, that's all right. Bella. Isabella. Do not see yet. I see Shamizi. Colin, you like to go by Max? Max, do I see you? Yes, I sure
here.
do. Okay, great. David? Liliana? Cesar?
I'm here.
Oh, you're here?
Yes.
Okay, awesome. Thank you. Eric, are you here? Eric Guerrero? I see Mohammed. Omar, do I see you? Do not see. Kristen? I see Mercedes. Mercedes. I see Nikki. Hi, Nikki. Do I see Justin? I do not see Justin. So the students I didn't see, so everybody's can check. I did not see Ernesto, Luke, Ian, Alex, Brendan, Joey, Justin, Isabella, Tiffany, David, Liliana, Eric, Guerrero, Omar, and Kristen. Are any of y'all here and I just didn't see you, which is my bad.
Did you see me, Shimezi?
Yes, I did. Yes, I did. Okay, awesome. I'll stop doing this and get onto our class. We're going to take a step back because in order to go from the average rate of change to the instantaneous rate of change, we need limits. So we're going to talk about limits, and then we're going to talk a little bit again about average rate of change, instantaneous rate of change, and then we're going to look at limits again. So the intuitive idea of a limit. Well, first, does anyone have a question that they want to ask before we get started?
How do we show you the homework from last week?
Oh, just show me on Wednesday.
Oh, yeah.
It'll be absolutely fine if you show me the homework on Wednesday. Thank you. Very good question. I'm taking a picture of.
What about if we upload it online?
Say again.
What about if we upload it online too?
Oh, then that's even better. Yes, good. That is absolutely fine. Was that Shamizi? Yes. Yes, absolutely fine. Okay. All right. So we're all good. No pre-class questions. All righty. So an intuitive idea of the limit is just thinking about it. First, let's look at it from the left. When the limit is said to be from the left, that means that the numbers that we're putting in are less than the number we're going for. So in this example, I couldn't finish getting these screenshots redone for our letters, but as we're getting closer and closer to A, X is approaching A from a position of being less than A. And if we're approaching from above or from the right, we're thinking of X being greater than A. And then approaching. So let's just first look at it from the left. if we're looking at the limit as x approaches a from the left, we're thinking of, we're traveling on this function. There's f of x. Is f of x getting close to this L as x gets close to a? Let's call AC since that's what we are using. But as we travel along f of x from the left side, and we're getting closer and closer to x equals c, does f of x get closer and closer to this L? In this example,
Yes.
yes, absolutely. So we would say that the limit as x approaches, let's use c since that's what we always use, from the left, a minus sign is from the left of f of x equals L. The idea of coming from the right means that first, and let's change this to a c also, it means that first f of x is bigger than c. So we've got some x over here. And as x gets close to c, does f of x get close to L?
Yes.
Yes, it sure does. In this case, it definitely does. So we would say the limit as x approaches c from the right or from above
Question,
x equals L. Say again?
are you going to send us your note, the note you're writing on?
Yes, I did already. I just sent them late.
No,
But
the one you are, the what you are writing on, the notes you are making right now. You'll be able to send it to us?
Oh, I usually let y'all have that, do that. The notations that I'm making,
Yes.
maybe this once I will. I usually assume that y'all will take notes on the notes. Yes, since we're having a bizarre day today, I will. Let me remind myself. Okay, I put a note to myself to do that. I want you to see just briefly why we're calling this an intuitive idea of the limit and not a formal idea. The formal idea for the limit is this one. Assume the domain of f contains the interval c comma d to the right of c. We say f of x has a right limit L at c, and we write this if for every epsilon greater than 0, there's a corresponding delta greater than 0, such that if f of x minus L is close to epsilon, that will be close to epsilon whenever x is delta close to c. And so there's a lot of stuff that we're ignoring. Do y'all see that? You'll see that? Okay, good. So it's okay for us to ignore it for a few days, but we'll definitely come back to that. Okay. Does everyone feel like they've got an idea of what we mean by the limit from the left and the limit from the right? Use the hand, the thumbs up or something. Yes, good. Thumbs up. I see 1, 2, 3, 4, 5. Ah, yay. Oh, I love it. Okay, great. So let's use that idea, that basic idea, to go through this really typical looking graph and answer these questions. In order to answer the first question, we have to answer several others. Okay, so we want to find the limit as x approaches -4 from below of f of x. So let's find -4. Looks like right here. we're approaching from the left. What is f of x getting close to as we go up f of x toward x equals -4?
One.
Looks like 1.
2.
I think it's supposed to be, oh, you're right, you're right. 1 is,
Yeah, I think he's right. I think it's 2.
yes, I think you're absolutely right. And what about the limit as x approaches -4 from the right of f of x? So that means we're coming from larger x values down, and along the graph, that means we're coming from the right side. Where is f of x getting close to as x gets close to -4? Isn't it also 2?
Yeah, wouldn't it be 2 as
Yes.
well?
Good, yes. Nothing here is trick. So, and if it doesn't make sense, just say so, because we can handle that. If, you know what, Shamizi, I really have to redo these notes today. So yes, I would definitely redo them and hand them out. If the limit as x approaches c from above, from the right of f of x, equals the limit as x approaches c from the left, equals some number L, then the limit exists. Limit of f of x as x approaches c exists. Let me read that again because it's a mess. If the limit from the right and the limit from the left are the same, then we say the limit of f of x as x approaches c exists and equals L. So if the limit from the right and the limit from the left equal the same thing, then we say that the limit of f of x as x approaches c without a plus or a minus on it exists and equals L. All right, well, what do we know then about the limit as x approaches -4 of f of x? Does that exist?
Yes.
Yes, because we got the same value for the limit from the left and the limit from the right. So it exists and equals 2. Yes, good. Now let's find f of -4. And f of -4 is
2.
2. That doesn't always happen. It doesn't always have to happen. When, let me find more paper because I'm just running out of paper. Here we go. When the limit as x approaches c from the left equals the limit as x approaches c from the right equals f of c equals L, then something special happens. Then we say f of x, pardon me. Then we say that f of x is continuous at x equals c. So if the limit from both directions equals L, and when you just plug in c into the function and you also get L, then we say f of x is continuous at c. Well, let's look at the picture. Does it look like the function is continuous right in this area? Do we have to pick our finger up to trace it? Let me make sure we're, I just had a scary thought that we might not be. Oh, we are recording. Okay, good. Phew. All right, so that means that f of x is continuous at x equals -4. Because we got the same value for all three, for the limit from the left, the limit from the right, and f of -4. All of them were 2. So that means that f of x, at least in that little area, f of x is continuous. And continuity for us right now, we're just going to think of it as tracing that little part of the curve without picking up our pencil. All right. Now let's look at 0. Okay. So we want to look at the limit as x approaches 0 from the left of f of x. So here's 0. What does f of x approach as f of x goes along the curve and x is getting close to 0 from the left side?
1.
I think it's also 2, but yes, it's the same. Yes, it's the same value. What about if we're doing the same thing, but we're approaching from the right? Sometimes people say from above.
2 as well.
That's right. Why are these all coming out the same? What's special about the graph at these x values compared to the graph at other places? Say it louder, Gabby. Danny, I didn't hear you.
It's a parabola.
Right in this area, yes. And do we have anything weird going on? Like if I look to the right of f of x, it looks like there's a lot of weird stuff going on. Is anything weird going on right around x equals 0?
There's a minimum.
It's a minimum, but do we have any gaps, any problem, any circles or skips or something strange looking?
It
No,
has
we don't have that
open
as we
dot.
approach 0.
That's right. And also when we were at x equals -4, we were at a part of the graph that didn't have any jumps or open dots or asymptotes. Okay, so what is f of 0?
2.
Good. That means 2 things. Let's write it out. Since the limit as x approaches 0 from the left equals the limit as x approaches 0 from the right, then the limit as x approaches 0 without a plus or a minus exists and equals 2. And furthermore, since the limit as x approaches 0 from the left equals the limit as x approaches 0 from the right equals f of 0. What do we know about at x equals 0? What is f of x?
It's 2.
It is equals 2, but what word did we say describes it when all 3 of these things are the same?
The limit exists.
So the limit exists if the left and right limits are the same, if also f of 0 is that same number, we said something special. So if the limit both directions and plugging 0 into the function all have the same thing, then we say f of x is continuous at x equals 0. We can't say it's continuous just if f of 0 has a value. We have to have something that we know around x equals 0. We have to have these two ideas of limits and it exists at 0. Does that make sense? Alrighty. So we said that the limit as x approaches 0 from the left and the right existed. So what is the limit without a plus or a minus?
2.
Good. And we also saw that f of 0 was also
Two of them.
good. The next one we want to look at, and I'm really tired of orange. The next one we're going to look at is when we get close to 1. And is that one more interesting? Let's look at as we get close to 2. So let's look at the limit. As x approaches 2 from the left of f of x. So here's 2. We're getting close to x equals 2. We're going along the x-axis in a northern position. That means that we're coming here along the graph toward what value?
Would that be 4? But it doesn't necessarily get to 4. If
It
it's
looks like it's
approaching
getting close to 5. But yes, it's this value, right?
I thought, oh, we're going from the, yes.
Yes, that's right. Okay, so the limit as x approaches 2 from the left gets close to 5. What about the limit as x approaches 2 from the right of f of x? So let's see, if we're going from the right, that means we're traveling the curve.
That would be 3.
That's right.
Well, approaches 3 whenever it gets close to it.
Well, the limit actually equals 3, even though the function doesn't equal 3.
Okay, so even with that little tiny circle, say, kind of showing that, okay, all right.
Yeah, because the idea is, it's like if you're on a train and you're going without a brake, but you've been going 55 miles an hour, you're still going to end up at 3, even if it doesn't exist. So yes, exactly right. What is f of 2?
4.
Yes. So now the question is, does the limit as x approaches 2 of f of x exist?
Would the answer be no because it's not continuous?
It's not because it's not continuous. It's because the limit from the left and the limit from the right are different. So that's a very good point. So it's no, since the limit as x approaches 2 from the left doesn't equal the limit as x approaches 2 from the right. The part that goes to continuity is when we add in f of 2. So is it continuous? Is f of x continuous at x equals 2.
No,
That's right. It can't be. When the limit doesn't exist, there's no hope. If the limit from one of the directions was the same as f of 2, like if f of 2 had been 3, or if f of 2 had been 4, then we would say, well, it's a little bit kind, it's a little bit all right. But since every one of these has a different value, then it's very not continuous. We'd say no. Is this sort of making sense?
yes, ma'am.
Good. Now their next one is looking at -2, and I've muddied up the graph, but I think that we can see it. So we want to look at the limit as x approaches -2 from the left. Let's see what's going on. Here is -2. It's the place where this vertical asymptote is. What is the function getting close to when x is getting close to -2?
It's an asymptote, so it never reaches -2.
So it's approaching, we would say that it's approaching infinity.
Okay.
That means, therefore, this limit does not exist and you'll find lots of sources, they'll put D in E, does not exist. And this is therefore the 3 dots. Is there any hope for the limit as x approaches -2 of f of x? Is there any hope for that existing? If one of the halves doesn't exist already?
No.
There's no hope.
That's right, very good. No hope. Can it possibly then be continuous there?
Yes,
No, it's like the lowest level is the limit exists. Continuity is on top of that. Later, we'll see that differentiability is on top of that. So our lowest level is the limit. Since the limit as x approaches -2 from the left goes to infinity, that doesn't exist. What about the limit as x approaches -2 from the right? What is that approach? What does f of x approach?
nothing.
It looks like it goes to infinity also. Does it look like it kind of?
Yes, it's an asymptote. It gets close to it as it can to -2, but doesn't necessarily reach it.
That's right. We don't care if it reaches it. All we care about is where is it going? Where is it heading? So we put does not exist. Usually does not exist if we're looking at just a left or a right limit. That means it's either going to infinity or negative infinity. So can the limit as x approaches -2 without a left or a right symbol of f of x, can that exist?
No, because it's infinite.
That's right. That's right. So we don't think of a limit existing if it's infinite. And since they're both infinite, there's just no way for the regular limit to exist. Since infinity isn't a number, it's an idea. anytime a limit equals an idea, we say it doesn't exist. It's not a number. Good. Do we have, so let's say, what is f of -2? So f of -2. There's -2. What is f of -2?
Zero?
Almost. If it were 0, we would have a
It's
dot.
2.
Yeah, there's a little dot right at 2. So f of -2 is equal to 2. That's what I mean when I say pasting a point. Do you see that they had an asymptote at x equals -2, and they just added a point right there? Did adding this point at -2, -2 all of a sudden make this area continuous? So let's write that down. Did adding the point -2, 2 make f of x continuous at x equals -2. So that's what we're wondering. And let's look at the image. They pasted or they added a point at x equals -2 for f of x. And we get the point -2, 2. Does that make this area of the function continuous?
No.
That's right. We still have, to the left and to the right, the function still blows up. It still goes to infinity. Well, let's look at a situation where that would help. What if we had this? Or if I could draw better, it would be helpful. Let's see. So what if we have this graph? This is f of x. And we're looking at whether or not, first of all, whether or not the limit as x approaches 4 exists. Which means in this case, we would want to look, I have to look for another pen. Here we go. What is the limit as x approaches 4 from the left side of f of x?
Three?
Good, very good. What is the limit as x approaches 4 from the right side of f of x?
3.
Good. What is f of 4?
3.
Almost.
I think it's supposed to be 6,
Yes,
but it
Oh.
kind of looks like 5.
there you go. Is that better?
Yeah, it's all better.
Okay. So it's not continuous at 4 because we got a jump here. Can we, by pasting a number, by pasting a point, in fact, by pasting this point, by pasting the point 4, 3 to the graph, of f is f of x now continuous at x equals 4. If we paste a point there,
No, because f of 4 is different than.
oh, okay, so I'm saying we're taking this point at 4 comma 5, we're taking it away. Very good point. Thanks, Eric. So we're taking this point at 4 comma 5 away, and we're adding the point 4 comma 3.
Yeah, I would make it continuous.
Yeah, we had a hole, and it's like we added putty and we filled in the hole. Is there a way to repair this kind of discontinuity where we've got an asymptote just by pasting a point?
No?
That's right. But we can paste the point all we want, but we can't change the fact that to the left and to the right, the function goes to infinity. In this example, in the other example, the function was kind to the left and the right. It wasn't blowing up. It was going toward a regular number. So it was not too hard to paste in the point 4 comma 3 and repair that hole. Does that make sense? The difference is pretty important.
I have a question.
Yeah.
So it wasn't continuous when it was 4 comma 5?
Yes, that's right.
Okay.
Because in order for it to be continuous, we need f of 4 to equal the limit from the right of f of x to equal the limit from the left of f of x. We need all three of those to be the same. So this says not continuous at x equals 4. That's a very good question, Mohammed. Thank you. So we're kind of doing several things at the same time. We're looking at what a limit is, and we're looking at what its implications are.
I have another question.
All right, good.
So like for no, not on that one, on the main example.
Yes,
Yeah. So for A, there is no point for on the B. So it says f of -4. What is that? You guys said it's 2, but there is no point.
oh, because it's on the graph. Since the graph itself is smooth, then we can say that at -4, f of -4 must be right there.
Okay.
So very good point. So we don't need it to look like a black dot in order for it to exist. Excellent, excellent point. Let's see if we can use this graph one more time. Let's find the limit as x approaches 8 from the left of f of x. So we're looking at approaches 8. I think we want 8. No, we want 6. So my bad. So I want the limit, find the limit as x approaches 6 from the left of f of x. So it looks like to me, 6 is 1 unit to the right of 5. That means as x is going to the right along the x-axis, f of x is going toward what value?
2?
Yes, very good. It doesn't matter whether it ends in a filled in dot or an open dot. Still, we're going toward the value x, f of x equals 2. What about the limit as x approaches 6 from the right of f of x?
3?
Yes, good, because from the right, we're getting close to f of x equaling 3. So, oh, and we have one more question. What is f of 6?
Would
Two.
that be 2?
Yes, very good. Since the filled-in circle is at x equal f of x equals 2, then we get the f of 6 is 2. So let's answer the 2 questions that we're thinking of. Does the limit as x approaches 6 without a plus or a minus of f of x exist?
Yes.
What has to be true for the limit to exist?
For the same number to be approached from the left and the right.
That's right. And we saw that from the left, went toward 2. From the right, we went toward 3.
So there's no limit.
Say it again.
The limit doesn't exist.
That's right.
There's no limit.
That's right. So is,
But I have a question.
all right.
Why is f of 6 2 instead of 3?
Oh, okay, good question. So my graph is really, really marked up, but here's 6. There's a filled in circle at 6, 2. And an open circle at 6, 3. That means the value of f of 6 is the dark circle.
Okay, the dot circle.
Yes, good question. Is f of x continuous at x equals 6?
No.
Good. It can't be continuous if the limit doesn't exist. But we can look at the picture and we can see, in order to go from below 6 to above 6, I've got to pick up my pencil. I can't trace along the graph without picking up my pencil. So it can't be continuous. Okay, those of you watching later and those of you at home, if you're watching later, just send me a text. But if you're watching now, just hold your answers for a moment. Actually use the text box, the chat thingy in whatever we call it, Zoom, the chat thingy in Zoom. If the limit as x approaches 1 of f of x equals 4, the limit as x approaches 1 from above of f of x equals 4, and f of 1 equals 3. We have that base. Does the limit as x approaches 1 of f of x, don't yell out the answers because the students at home are going to get to text me this answer. So first, does the limit as x approaches 1 of f of x exist? If it does, what is it? If it doesn't, just say it doesn't. And then is f of x continuous at x equals 1? Yay, I see answers coming in. Oh, this is exciting.
Is it direct text message?
Pardon?
Are we going to send a direct message or to everyone?
Send it in the chat. There's a chat function in Zoom. Some of y'all are putting one word answers. We've got two questions. Does the limit exist? And is the function continuous? So put two answers. Okay. Good, Max. Okay. So some of y'all are getting it and some of you aren't, but that's okay. So I'm gonna pause the recording and answer y'all, and then please help me remember to restart the recording. See? Good. So give me a thumbs up or something if this is making sense, and a thumbs down if you'd like us to go over it more. Okay, awesome. No thumbs down. Oh my gosh.
Can you go over it one more time, please?
Of course, let's do it with this last example. Let's look at this function, f of x, and I'm going to say that that's 5. And let's call this 3. Let's call this 5. So what is the limit as x gets close to 5 from the left of f of x? What part of the graph are we looking at?
That's right.
Yeah, the part on the left. And what is the part of the left getting close to as x gets close to 5 from the left?
3.
Is it 3?
Yes. Yeah, that should be a 3. Good. And what is the limit as x approaches 5 from the right side of f of x? And let's go back to the picture. So the part on the right side, is that the part that's higher up or the part that's lower down?
Higher up, so it would be 5.
Now 5.
Excellent. So now don't tell me text, use the Zoom texting thing, the Zoom chat, and tell me, does the limit as x approaches 5 of f of x exist? I'm going to get a new pen. These pens don't last very long, but I like them. And the second part is, I can't write, but that's okay. Is f continuous at x equals 5? So don't tell me, just use the chat to answer the two questions. Does the limit as x approaches 5 of f of x exist? And then is f continuous at x equals 5? And let's look at the picture again. Good, good. Good. Yay. Is this making a little bit more sense? Good, very good. So there are so many layers of what we're looking at. And the reason why limits are confusing to some students is that we have to look at all those levels at the same time. So now that we've exhausted this picture, I want y'all to do a couple of questions with your, together. I'm going to go away and I want y'all to work out, oops, okay. This is my bad. I want you to find the limit as x approaches -3 from the left of g of x. This is g of x. The limit as x approaches -3 from the right of g of x. And then here are the last two parts of that question. And then let's add two parts to this approaching -2. Find the limit as x approaches -2 from the left of g of x. And the limit as x approaches -2 from the right of g of x. Oh, and there's one more, there's that 0. So find the limit as x approaches 0 from the left of g of x, and the limit as x approaches 0 from the right of g of x. So first the left and the right, and then the limit without the left and the right, and then find the actual value at the point. And some of those may not exist. Okay, now I'm going to go away. Well, are there any questions about what I'm asking y'all to do? All right, I'm going to go away and I'm going to pause the video. So please, please, please remind me to restart it.
What's it called? Doesn't exist.
Very good. Very good. So let's fill in. You said the limit of g of x as x approaches -3 from below is
-2.
-2.
excellent. The limit as x approaches -3 from above of g of x.
-3.
-3.
-3.
And the value of the limit without the plus or the minus. Does the limit
-2.
approaches
That would be -2.
So without the plus or the minus, does the limit exist?
No.
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 Does not exist. DNE stands for does not exist. And what is G of -?
-2.
Good. And now tell me what you found for the limit from below as x approaches -2.
We said it's about. -2.
Good. And the limit as x approaches -2 from the right of
Neg-
G of x.
-2 as well.
Good.
And then g of -2 would be -2 as well. So the limit is -2, and then
And so what can you say about
it's continuous
G of x is continuous at x equals -2?
at -2. Okay.
At x equals -2, G of x is continuous. And we can say that, let's part of that, continuous, since the limit as x approaches -2 from the left side equals the limit as x approaches -2 from the right side equals G of -2. And they all equal 2. No, they all equal -2. Okay, good. So since all of these are the same value, then the function is continuous at that point, at that area. Okay, now what did you find for the limits going towards 0? From the left.
It's infinite since it never totally approaches 0 and continues on.
Good. And the limit as x approaches 0 from the right.
Is 1.
Excellent. The limit without the plus or minus as x approaches 0 of g of x.
Does not exist.
Good. And what does it need in order to exist?
They need to equal out. So infinity does not equal 1.
That's right. They need to equal the same thing. Certainly, they both need to exist. So what is g of 0?
1.
Good.
And is not continuous.
Not continuous, yeah. Where is this thing continuous?
From 1 on.
That's right.
When x is
Yeah, from 0 on. And between -3 and 0, because this will get as close to 0 as we want. But at 0, no. What about if we look at the graph below or to the left of -3? Is that continuous?
yes, unless it flattens out sometime after.
Right. So functions can be continuous some places and can not continuous other places. And depending upon what made it not continuous, sometimes we can fix it. Okay, for each of these limits that they're asking, I want you to find the limit from the left, the limit from the right, and then answer the question. And actually, let's do this one together because I see something that we haven't talked about. So let's look at the limit as x approaches 2 from the left of f of x. What are we going to get?
Two.
2.
2.
What is the limit as x approaches 2 from above or from the right of f of x?
1.
That looks like 1, yeah.
What is f of 2?
1.
Does the limit as x approaches 2 of f of x exist?
No,
That's right. Why not?
because from the left and the right, they don't meet at the same number.
That's right. So what we need in order for the limit to exist is that we need the limit from the left and from the right to be the same. We did not get the same. We got 2 and we got 1. What does the value of the actual point add to this? If we got the same value for all 3, what would that one add? In other words, do we need f of 2 equals 1? Say we had the limit as x approaches -2 from below of f of x is 1. Say we got 1 for the first 2 answers. Do we need the value f of 2 to be 1 in order for the limit to exist?
No,
No.
We do not. That's correct. What does it give us if all 3 are the same though?
It makes it continuous.
That's right. So we add continuity if the function exists and has the same value at the point.
Can you repeat that?
Yes. So in order for the limit to exist, we don't really care what happens at the point. We care as we get close from the right and close from the left that we get the same value. So say we're both 1,
Okay.
the limit would exist. If also we get that f evaluated at that number is the same number that we got for the limits, then we add continuity.
So there's a continuity if f of that number is equal to any of the two values.
Yes. Now let's look.
And the same thing, at the same time, if three of them are equals, then there's a continuity.
I couldn't quite hear you. My hearing is not great anymore. Say again, please.
So so you're saying there are two stages where there will be continuity when the three are equal, and when f of 2, let's take for example, is equal to any of those from the left or from the right. Is that what you're saying?
They all have to equal, yes. So if the limit from the left and the limit from the right and f at that number are all the same, they all have to be the same, then yes, then it's continuous.
But from the last, from what you explained last, f of 2 is equal to 1, which is equal to 1 of f, when it tends to 2 from the right,
Hmm.
and it's what you said there's a continuity right there.
Oh, no, I was saying if the limit from the
Okay,
right had been 1,
okay,
so I was saying, if we had this image, f of x approaching also the value of 1 from the left, then we would have 1, 1, 1 for every answer. Then we would have continuity.
okay. But right now there's no continuity, right?
That's correct. Very good.
Okay.
Okay, now we have a strange situation, and there are two ways to look at it. So if you look at the domain of our function, it looks like it starts, the world begins at 0 and the world ends at 4. If you look at this world that way, if you say, that the domain, that the domain of f is 0, 4, then you would say that the limit exists and the graph is continuous at x equals 0. And also the limit exists and the graph is continuous at x equals 4. However, if the world is bigger, if the domain of f is everything, in other words, the whole regular, all the real numbers, then we don't have the limit existing because there's nothing coming from the left for the x equals 0, and for the x equals 4, there's nothing coming from the right. Do you see the difference in those two questions? So if the entire world, the domain is like the world, if the entire world begins at 0 and ends at 4, then everything is good in this graph except at x equals 2. However, if the world extends past 0, below 0, and above 4, then we only have one direction at x equals 0. We don't have anything coming, no part of the function is coming from below x equals 0. And we only have half of the graph at x equals 4. Nothing is coming from the right. Do you understand the difference between those two ideas? Okay, Danny says yes. Thank you, Danny. So the idea, what I'm trying to share is, here's the whole world. Here's the domain of f. In that domain, We have that image. Say we have that image. Do we really care that the graph goes all the way to the edge of the world?
Yes,
Well, we don't care if it actually does go to the edge. We would only care if it didn't. Like if it isn't defined everywhere. However, if we've got the domain of F, this is the image for the domain of F starting at 0 and ending at 4. If the domain of F is all the real numbers, you can use a double bar on the R. That means all real numbers. That would mean, excuse me, that we only have a little bitty part. There's F of X. I can see that it's sort of, F of X is kind of behaving correctly or nicely, not at that endpoint, but in between. And on the right side, F of X is behaving nicely between the endpoints, but not at the endpoints. Because what's going on here, what's going on below this lower endpoint, what's going on above the upper one? We don't know. But we need to know in order for the limit to exist. Both limits have to be there. Do you see the difference in these two scenarios? Okay, swell. Oh, I did this example because I wanted you to see what pasting looks like. Because we talked several times, we've talked about pasting a point at a discontinuity. So here I've got the function f of x is equal to x squared minus 1 divided by x minus 1. And I can see that as x gets close to 1, I'm definitely, the function does not exist at 1. F of x does not exist at x equals 1 because we have 0 over 0. If we assign a value to the function, because it's the same function, but we say, well, at 1, at the place where the first function isn't nice, let's decide that x of 1 is 1. We're allowed to do that. So now I can see that the limit still exists. Did I make it continuous? Is g of x continuous at x equals 1?
Yep.
However, if we let h of x be defined this way, it's x squared minus 1 over x minus 1 for x not equal to 1. And it is 2 at x equals 1. What does that do to our graph?
Makes it continuous.
It fills in the point. So we can fill in the point. That's what happened in g of x, but we didn't make that point coincide with the rest of the function. We can fill in the point like we did in h of x, where that point coincides with the rest of the function, and we've made it continuous. Does the limit exist at 1 for g of x?
Yes.
Yes. Does the limit exist at 1 for f of x? In other words, from the right and from the left, do we hit the same value?
Yes.
Yes. So the limit, good. The limit exists for f and for g, but they are not continuous. But when by pasting the right point, by pasting a point at 2 comma 1, 2 comma 1, or at 1 comma 2, my bad. So this is 1 comma 2. Then we not only have the limit existing, but we also have continuity. This kind of discontinuity is called removable. All right. I just want to check something really quickly. The homework is at the back of the notes. For each of these questions where they're asking about the limit, each of them, I want you first to find the left and right limits. And then answer the bigger limit question. So for each one, for A, C, E, G, I, and K, find the left and right limits first, then answer the bigger question. And the same thing with, oh, this should be A, B, C, sorry about that, E and F. So again, answer by finding the left and right and limits first. And then finally answer 2 questions. I can't write though, 2 questions. Does the limit exist? At X, at the value, and is the function continuous at the value? And I'm gonna type this up so that you won't have to remember these, but I'm gonna add these questions to the top. So for Wednesday, I just want you to do 1 and 2, but I want you to do a lot with 1 and 2. Does that make sense? Awesome. We still have, thank you, Eric. We still have some time, so let's look, see where we are. Okay, let's look at example 5. I think this is where we are.
I have a question about example 1.
Yes. Oh, which one?
Example 1,
The one that we did. Here.
the first one. Yeah. So what would be f of 10? No, wait, what? No, not this one. The first example that we did.
This was the first one we did, I think. Yes, that's the first one we did.
No, it's different. Like the graph was.
We also did this one.
There should be another paper.
We did this one. Oh, you're so right. Oh my gosh. I have two things labeled one. You're so right. Okay. Yeah, so here's the first example.
Okay. So what would be f of 10 or f of 11?
So here f of 11 is not defined. So the limit can exist, but the function might not be defined. Like at, what is this? 6, 7, 8. Let's say that this is 8. At f of 8, the function isn't defined, but still the limit exists because both directions are going toward, I guess that's 3.
Yeah.
And at 11, the limit doesn't exist because from the left, we're going toward 3. From the right, we're going toward 5. And again, f of 11 doesn't exist.
Okay, got it. Thank you.
Welcome.
Can you explain what you mean when you say it doesn't exist?
So there's several things we're saying doesn't exist. Let's look. So, and in fact, we have a few seconds. I'm going to print out a cleaner copy of that because it's really a mess. That's on page 1. Okay. Is this a little easier to see? So which one were we talking about? F of 11?
10 and 11, yeah.
So here's 11. And I want to look also at f of 8 and pretend that this dot above on f of 8, I'm going to pretend that dot is not there. So that dot is gone. So I would say the limit as x approaches 8 from the left, this is f of x, equals the limit as x approaches 8 from the right, and they both equal 3. But f of 8 is not defined. We're saying they didn't assign any value to f of 8. Here, the limit still exists because we have the same number from the left and the right. So now let's look at 11. Also with 11, we see that f of 11 is not defined. There's no filled in circle. The limit as x approaches 11 from the left, what is that value?
Is that 3?
Yes. And the limit as x approaches 11 from the right,
5.
good,
That's 5.
good. So here at 11, the limit doesn't exist and f of 11 isn't defined. At 8, if we get rid of this point above 8, we would say that the limit does exist, but f of 8 isn't defined. So the limit as x approaches 8 of f of x exists and equals 3, but f of 8 is not defined. This would be the kind of discontinuity that could be repaired by pasting a point at 8, 3. That's actually a huge amount of information. We have a few minutes for questions. And I, again, want to make sure that y'all feel good about the homework. Well, it's somewhere. Who knows? So all I want you to do for the homework is questions 1 and 2. And they're quite long. So only do questions 1 and 2. From assignment 3. And find for each one and for each limit, find the left and right limits first. I promise I will post these better notes. Oh, I found it finally. But oh no, this is rules of excellence. That's what happens when you're teaching so many different things. So I promise I will repair the notes before I add in all the extra stuff that I said. I'll make sure that the notes actually say that you should do these things. And as soon as possible, I'll get the corrected notes up with all of the words I said. Is that groovy? Is everyone groovy? Yes, thank you, Danny. Eric, Santiago, anybody else groovy? Christopher, Mohammed? Yes, yay, yay. Christopher, yay, Santiago. Yay, Blossom, thank you. Okay, thanks, Mercedes. All right, groovy, thanks, Christopher. So I'll send it out again, what the homework is, and I'll clean this up. Are we all happy? I hope. Great. Well, have a wonderful, I almost said a wonderful weekend. Shows you how discombobulated I am. See you Wednesday.
Thank you.
Thank you.
Miss
Thank
Nell,
you.
Yes,
oh, do you have any office hours today?
only by appointment. So if you want to have office hours, let me know and I will.
Okay. Because I was looking at your the syllabus again just to like refresh, and your office hours start at 3. So do you think I can make an appointment with you between like your office hours today or no?
Oh, yeah, sure. The only reason I'm asking for an appointment for today is that I've got to deal with my car at some point also.
Oh no, yeah, definitely. We can do it later in the evening, like around I think it was like 7's the latest, so like 6 o'clock.
Sure, absolutely.
Okay, sounds good.
I'm putting you in for 6, is that right?
Yes.
Same Zoom link.
Okay. The one you sent out, correct?
Yes.
Okay, awesome. All right, then I will see you at 6, ma'am.
Okay. Thank
Bye,
you.
Miss Nell. You too.
Thank
Bye.
Shimizu, did you have a question?
Yes, ma'am. On which chapter should I find this on the textbook?
Say again?
The topic you just treated, on which chapter will I find it on the textbook?
Oh, our textbook has all of this in 2.1, the first section of chapter 2.
2.1?
Yes, let me upload again. Here it is. The URL for our text. I'm going to send it to you really quickly.
Okay. I guess you're still recording.
Pardon?
It looks like you are still recording the Zoom.
Thank you. I'll stop.